So I'm Mikey, third year on the ethical hacking programme up at Abertay. Pro tip, don't fail your second year because Dundee sucks. This is what it looks like, thanks to Gavin and Duncan if they're kicking about. I'm also a member of the Ethical Hacking Society up there. We have our illustrious Vice President looking very hungover up the back there. I'm into cryptography and defence. If you want to debate why we should TLS all the things or why we shouldn't, find me or Gavin Holt later. We will talk for days about that. On a side note, I'm quite into the whole national security thing, so counter-extremism, counter-terrorism. Again, if you want to chat to me about that, I'll speak to you for hours about ISIS. You can find me on pretty much everything at MikeyJCK. Quick 10-second plug, did this last time as well, but the Ethical Hacking Society, we run our own conference up in Dundee. We run it, when are we running it? February, like late February 2017. We were 2 days when we ran it this year. I don't know what we're doing this year because, again, our Vice President's always drunk. We have an after party. We're about 300 attendees at capacity. It's a good time if you fancy come and get drunk and doing some hacking in Scotland. Sweet. So I'm going to open with just a bit of background on what crypto hash functions are. Talk just briefly about password cracking and why we don't want to be using hash functions for password storage. Talk briefly again about key derivation functions and what I recommended last year. That's in the wrong order. Talk about the password hashing competition, talk about its winner, Argon 2, and then finally talk about hash upgrading, or how we can migrate from old broken functions to new ones. So this is the obligatory XKCD, right? 4096-bit RSA, that's fine because we're going to drug him and beat him to death with a wrench or until he tells us the password. So why do we care about this? Just quickly. Well, that wonderful time Adobe was hacked, right? And we got like the best crossword puzzle ever, where we got the password hints, and some of the passwords were in MD5, some of them weren't, and who knows what the hell they were doing with the rest of them, right? So I think now if you go on to haveibeenpwned.com, I think Troy Hunt's indexed like 1 billion, just about 1.1 billion sets of usernames and passwords, right? As far as I'm aware, the sort of active set of real human-created passwords that are kicking about is somewhere between about 1.5 to 2 billion, right? So we have a pretty big data set for this sort of thing, and people get broken into all the time, right? Talk, anyone. So, we're going to just briefly cover, well, not briefly, but we're going to cover what hash functions are and why we use them, right? So one-way mathematical function, so we have some input that we pump through this algorithm. It gives us a fixed length output, the digest, right? And the reason that we like this is it's a compression function essentially, right? So we take some data of arbitrary size and we can compress it down into 160 bits if you're using like SHA-1, 256 bits for SHA-2, right? So you have basically D, your digest, and some function in your input. Again, your common algorithms here, SHA-1, SHA-2. The latest in the SHA family is SHA-3, or Ketchak, which is a bit of an odd one because we thought kind of that SHA-2 would be much more broken than it is at this point now. So SHA-3 was introduced to complement rather than replace SHA-2, so that's a little bit odd. But as far as we know, there's nothing wrong with SHA-2 at the moment, right? So from our cryptographic hash functions, we expect three things: pre-image resistance, second pre-image resistance, and crucially collision resistance, right? So just briefly on these, pre-image resistance, given some hash value D, it's difficult to find another message M such that D is equal to that M, right? So essentially what we're saying here is that it should be difficult for some definition of difficult. So the definition of difficult is basically beyond reach of the adversary that we want to break the system. Or you can start talking about things like P equals NP and get into asymptotic polynomial time, which we're not going to do because I had far too much rum last night to start talking about that, right? But basically this is the principle that given a hash, it should be difficult to find some other message that created that hash, right? Second pre-image resistance is a bit of a technicality. So for some fixed input M1, so we give the attacker an input that they can't change. They have to essentially find another input M2 which will produce the same hash, right? So the difference between this and a collision is that M1 is fixed, and then the one we all know about, collision resistance. So given any input M1, it should be difficult to find another input M2 such that the digest at M1 and M2 are the same. So this is what most people understand about hash functions, right? So if you have a file, any small subtle change, so these were created pretty much right after each other, so the metadata is not that different. The better way of doing this would have been to echo into SHA sum, but I only thought about that after. So you can see here that the only difference here is one character, but you have a radically different output of the hash, right? So there was quite a lot of talk recently about SHA-1 being very broken, right? So the free start collision against the full 80 rounds of SHA-1 was pretty much the first actual attack we care about on SHA-1, because again it was against the full 80 rounds. So Mark Stevens, he pretty much loves breaking hashes, right? You can go get his tool hash clash, and you can go run that on your PS3 cluster that you obviously have kicking about the house, and you can try and generate your own collisions. So what a free start collision basically, in the Merkle Darmgard construction, we have a message block, and then you have a chaining value, or your initialization vector, right? So the first block, we don't have a chaining value, so the chaining value is usually the block that comes before, right? But the first block we need to supply an IV, right? So the free start collision basically means that under some scenario the attacker can control the IV, and if they can control the IV, then they can create a collision, right? So I think the IV that they found differed by like 4 bytes or 2 bytes, right? I mean, it's quite a nice attack. It shouldn't really have us worried about SHA-1 hugely. The context that we usually talk about is certificates, right? So to go from some arbitrary M1 and M2 collision to a collision involving certificates, the order of magnitude against colliding to get a certificate collision is orders of magnitude harder, right? Because there's a lot more variables at play. Having said that, you should be moving away from SHA-1. The MD5 free start collision was found in '96, and we didn't have a full break against MD5 till 2004. Again, having said that, the CA browser forum, right, if you ever want to just see a clusterfuck of InfoSec, go look at what they debate. The CA browser forum basically want to deprecate SHA-1, which we're doing, but then you have Symantec on the other hand, just minting new certs with SHA-1 for super special vendors, right? So having said that, you should be moving away from SHA-1 to SHA-2 and anything new that you're implementing, right? So one of the other core things about hash functions is that they're efficient, right? Very, very quick. So you're talking, tenths of a second to generate something, right? So the problem here is that we can just go buy a Titan X, and we can compute like billions of MD5 a second, or hundreds of millions of SHA-1, right? So the sort of state of the art at the moment, if you're looking to brute force, you're looking at an upper bound of about 10 to 12 characters, and then you're really talking about the realms of impossibility. Even in the range of 10 to 12 characters, you're kind of fishing in the dark, right? You're going to have a lot of reason to go after someone with a password of 11 characters with a brute force, right? The other thing here is that it doesn't matter what your underlying function is. If your password is password 1 or a day of the week 12, we're going to crack it, and we're going to crack it pretty quickly, right? This is quite nice. I think this is from 1Password's sort of password generation thing. So they've moved from giving you just a mishmash of nonsense to this sort of, dictionary words separated by special characters. Now, I don't remember exactly, but I'm pretty sure that their list of dictionary words is public, right? So while it's great for memory, it's probably not great in the long term, because the people that do password cracking, not myself, but they're generally pretty clever, right? if you go onto the Kraken forums, like after the full LinkedIn breach came out, they cracked like 86% of that dump in like 4 or 5 days, right? So these people are pretty clever, and this sort of thing I don't think is going to fly for very long. And power to price ratio, right? So this is Jeremy Gosney, I don't know how you pronounce his name, but his company, Sagatia High Performance Computing, they specialise in rigs built for password cracking. So this is their sort of monster rig, Brutalis. So 8 GPUs, a couple of Xeons, like 32, 64 gigs of, you know, badass ECC RAM, right? It'll set you back 20 grand, but you will be able to compute 200 billion MD5 a second, or like 687 million SHA-1 a second, right? These actually are the benches, his latest benches on the GTX 1080 for any graphics cards enthusiasts, right? So that's pretty impressive. So we need something a little bit slower. So what we have is, what we came up with was key derivation functions. So the fundamental principle here is we just iterate some cryptographic function. So it can be an underlying hash function or a block cipher. And the standard model of this has been kicking about. I think the paper was like Bruce Schneier in '97, I believe. But the standard model is that you have some search space, 2 to the s, and we basically want to extend that by t, which is where we get t from our iterative function. So then the attacker has to search 2 to the s plus t, right? That's basically the standard model. So this is one of my slides from last year, and this was like my second or third last slide on what we should be using. So back then, the state of the art for this was PBKDF2, password-based key derivation function 2, or SCRYPT, right? So OWASP and NIST, I believe, have standardized PBKDF2, and basically I said, you know, if you need to be FIPS, if you need to be compliant for whatever reason, you probably want to use PBKDF2, but if you're ultra paranoid, so for those of you that use Keybase to manage your PGP keys, I don't know if their UI still does it, but they've used SCRYPT from day one, because they obviously take, if you want, they take your private key. The guy that designed this, Colin Percival, is a security, or is one of the security officers for BSD, and the reason he created it was he runs a backup company called Tarsnap, and he basically builds Tarsnap as the sort of cloud backup service for the ultra paranoid, but that's somewhat of a paradox in and of itself. But anyway, the goal here was to replace PBKDF2, and at the current time bcrypt was the other sort of state-of-the-art key derivation function, right? And its primary goal was to be memory hard. So this is interesting. There's a really long there's quite a short actually, but I'm not going to start getting mathematical formulas out because, quite frankly, I just don't like math. But basically, you want an algorithm which uses almost as many memory locations as it does operations, right? So for the number of clock cycles that we're using per byte, we should be using a similar amount of RAM. So that's on a random access machine. So sequential memory hardness, essentially the same thing. But we don't want it to parallel well either, right? So you should use some large amount of RAM, and when I say large, you're talking like a kilobyte of RAM here is what we regard as a significant amount of RAM, and it shouldn't parallel well, right? And so this other requirement here was sort of introduced with Argon 2, we're going to talk about that a bit later, but essentially, if there's a low amount of memory being used, we should up the clock cycles per byte to compensate for that. And one of the main attacks here is time memory trade-off, right? So if your problem can be solved quickly but requires more memory, you can spend more time and less memory, right? Or you can use more memory and solve the problem more quickly, right? So the classic example of time memory trade-off is rainbow tables and lookup tables, right? You do some amount of pre-computation, so then you only have to check against your list when it comes to the Kraken rather than doing the computation on the fly, right? So at the time, SCRYPT was pretty state-of-the-art. Colin Percival, pretty smart guy, right? But unfortunately, in terms of what we like as so what cryptographers like, just to clarify, not a cryptographer, definitely not a mathematician. I can barely tell the time most days, right? But what cryptographers like is simplicity. So PBKDF2 calls SMIX, which then calls ROM mix, which calls block mix, which calls salsa 20, and then we pump that back into PBKDF2. So in the beginning here, we take our password, we pump it through PBKDF2 to get a bit stream, we then feed that into SMIX, that goes into ROM mix, blah blah blah, and then we run one last round of PBKDF2 at the end to get our password, right? Now, unfortunately for SCRYPT, ROMIX is a side channel, so if you have some SPI process on the machine that's running SCRYPT, you can, using cache timing side channels, you can basically compute the passwords faster by looking at how the memory locations that SCRYPT is accessing, and you can pre-compute these, right? So it had 3 parameters: your CPU memory cost, RAM block size, and then some parallelization factor. The other nice thing here is that it's all done in 32-bit math, so one of the sort of requirements of slowing it down and not parallelizing well is 32-bit math, right? And I think SCRYPT at the time when he first benchmarked it, Core 2 processors, it was about 1 byte of RAM to every 10 clock cycles, right? So password hashing competition was initiated, I think, in 2012. The best way to do anything by consensus for cryptography is to have a competition. It's basically like a roller derby in that people submit their candidate, and then once we have the list of candidates, all the submitters try and break each other's ciphers, along with some panel of subject matter experts who will try and break the candidates, right? So the other interesting crypto competition that's running at the moment is the Caesar competition for a new authenticated cipher to replace GCM, because as Hanno Block and co just showed at Black Hat, there are some problems with GCM. It's not a panacea, but while we're talking about that, just anything less than TLS 1.2 within a head cipher is broken. So yeah, I think that slide's in the wrong place. We'll just but yeah, passwordtachhashing.net. Same sort of idea as NIST competition for AES. So the panel, so some of the names you might recognise. It was initiated by Jean-Philippe, however you say his second name. Jeremy Guzny, again the guy who owns Sagatia. Matthew Green, you probably know, crypto professor from Johns Hopkins. Colin Percival, again creator of SCRYPT. And Zuko Wilcox O'Hearn, who is the guy doing that new cryptocurrency that looks really cool. I forget what it's called. So their basic goals here. So they had 24 candidates initially. 2 of them were withdrawn, so they ended up with 22 candidates and about 9 finalists. But the goals here weren't anything really wild. They basically wanted something that had a simple construction in terms of cryptographic primitives, and something that was easy to implement, right? Because as we just saw from SCRYPT, calling like 8 primitives nested inside each other, not a fun time. The primary goal in terms of security was to be resistant to massive parallel GPU or application specific integrated circuit cracking, right? They wanted side channel resistance, and they wanted resistance from time memory trade-offs as well. And crucially as well, in terms of end use, they wanted the parameterization to be pretty simple, right? So the only 2 knobs you can use, that you should be using to tune this, are memory and time, and we'll get into that. And again, the last sort of requirement of this is that the function itself and any underlying functions should be patent and royalty free for the greater good of the community. So initialized in 2012, their CFP ran for a year, closed on March 31st. They announced their finalists in Q3 of 2014. Ironically, at the time I gave this talk, or the first version of this talk in 2014, I actually had no idea this was going on, which kind of sucks, but hey-oh. And then they announced the winner on the July 9th of last year. So the winner was a function called argin2. Argin2 was designed by some lovely Belgian men, although the number of primitives that we have in cryptography designed by Belgians is really disproportionate, right? I mean, they keep designing really good crypto. The current latest version of this is 1.3, and we're going to talk briefly about some of the other versions and the problems they had. So the possible input parameters for this, so we only actually care about P and S for the most part, so your message string, your password, and your nonce. So again, we'll get into this, but a salt is required. But you have your message string, your nonce, your degree of parallelism. So the parallelism is what defines how many independent compute chains you run, right? Independent compute chains, but they do synchronize. We'll get into this. Your M is the maximum amount of RAM to be filled in kibibytes. T number of iterations, so that's your time parameter. And then you can use secret keys with this, so you can use it as a keyed function as well. And then some associated data up to some arbitrary length. I think it's some length like 32 bytes. So this is me trying to understand like the 3 papers I've been reading on this on my whiteboard, and then Niall just graffitiing up there. Cheers for that. So at quite a high level, how it works, so we set up H0, so H0 is a 64-byte value, and we run some hash function over all these values. So the values are taken and we spin the values into their 32-bit integer representation of whatever the value is, and then we run some hash over it. In the case of Argon2, they use the Blake2b function. So Blake2b was designed by the guy that initiated the competition, and they've actually just in the last few days announced a new version, or produced a new version of Blake for the scrutiny of the wider community. So we run a hash function over the password, the salt, and all the other parameters, and we get some 64-byte value, right? So the sort of the legwork comes in here, where we take a 2D array, so a byte array with I and J in it, and then we fill m number of m amount of RAM. So that is the memory, the maximum amount of RAM that we defined in the input parameters, right? We take that number of 1024 byte blocks, and then we sequential dependent. We fill that array, right? So the first BI0 and BI1 are dependent on the initial 64-byte value that we get from hashing all this, and then from then on, the blocks are dependent on what came before, essentially. So this is great, and this is from the RFC, so the Internet Engineering Task Force, the Crypto CFRG, the Crypto Forum Research Group, have recently produced a draft RFC for this to standardise it, and their RFC, if you're not into math or cryptography, is great to go read, because they have lovely diagrams like this that helps you explain it, right? So the reference implementation uses 4 memory slices. So the slices are basically how we partition RAM, and then we have P number of lanes. So again, the number of lanes is defined in your parallelism factor, right? So in each slice, they're computed in parallel, and they can't reference blocks from other slices, right? But all other blocks can be referenced, right? Because if they could, the way I understand it is, if they could reference other blocks, that would introduce a side channel of some sort, right? So this is when Aragon is doing a single pass, but we'll get into that as well. So basically, we fill this 2D array over and over again for some t iterations that you pick. We XOR the previous block with an X block, and then the hash is returned as a tag of the last column, right? So your last block C is XORed with our last column from here, right? And then we return the tag, again, our hash function, underlying hash function, Blake2, over the C column, and then that returns our tag, right? So sweet, we've just done some not very complicated math. It's actually a family of hash functions, so there's two variations, so there's 2i and 2d. It's very memory hard. You can fill a gig of RAM in like a fraction of a second, right? The parameterization that we only really care about in terms of deploying it is the time cost, or memory cost, and the parallelism. The actual paper and the RFC provide recommended input parameters for various applications. I'm not going to get into that. If you want to deploy it and you're writing it in code, you probably just want whatever the crypto library you're using is picked, unless you're doing something pretty crazy with it, right? And yeah, the IETF CFRG are trying to standardize this, right? So the two sort of versions exist for really good reasons. So 2i, the next block, when we're filling this 2D array, the next block is independent of the password and salt, whereas argon 2D, those blocks are dependent on the password and salt. So 2i is vulnerable to 2D, sorry, is vulnerable to side channels, right? Because we can pre-compute the memory locations, right? So if you're using I, you probably want to be using that in your adversarial setting. So that is your client, and then 2D can be used in things like cryptocurrencies for proof of work and this sort of thing, right? So D is the faster of the two, but it aims for greater GPU and ASIC resistance. So it's far better at resisting time memory trade-off attacks, right? Yep, just said that. That's great. Yeah, so if you're using this for passwords, key derivation, you want argon 2i, right? Or even if you're not doing key derivation with it, if it's in an adversarial setting or anywhere that the adversary can readily access the RAM or the CPU, you want to deploy I, because it's designed to be resistant against these sort of side channels, right? So the performance is pretty good. You can go to the passwordhashing.net, and they've got the reference implementation, and they also have like a nice little command line tool, and you can go and play about with it, and you can pump the RAM up to like more RAM than your computer actually has, and watch it almost kill itself. That's fun. But it's heavily x86 optimized, so again, it's designed to really withstand ASIC attacks. So when we talk about x86 optimization, things like the latest register design in the Intel and AMD CPUs, so there's actually a bound penalty on the registers, a clock cycle penalty. So if you're the 128 and 256-bit registers on Intel processors, for example, if the memory locations don't match up in, I think it's 16-byte segments, if these are off, so if you're implementing this on specific hardware, then it imposes a clock cycle penalty to try and deal with that, right? They also designed it against the sort of latest, the latest Intel and AMD processor sort of quirks in memory synchronization, right? So they aim for it being able to parallel well, but for the amount of RAM to increase, because we want to take advantage of the ridiculously 40-core chips that AMD are making, but no one's buying, right? So yeah, again, that graph pretty much, that table pretty much tells you what you need to know. So their little command line tool is quite nice. You can go play about with that. I should have mentioned this earlier, but an independent salt is required for each password, and it will just straight up refuse you if you don't give it at least an 8-byte salt, which I think you can see, yep, up the top. They recommend 16-byte salts, but I think it goes up to 32 bytes, I believe. Yeah. So it has a couple of nice features tacked on the end of it as well. So it's got native hash upgrading. So hash upgrading in this context is if you have the iteration count set at 1,000. So if anyone's ever used LastPass, where they let you choose your own PBKDF2 count, and at some point in the future, that iteration count will become insecure. So we want to upgrade the iteration count without having to request a password from the user, This will do that, no problem. It's built in, which is really nice. It also has client-server handoff. So this is again where the dual independent and dependent implementations come in. So if you have, for example, an IoT device that you don't want to kill by doing, hundreds of thousands of iterations of some random crypto function that I'm telling you to use, you can basically compute the first 64-byte value on the client, and then you can do some black magic to that, ship it off to your server, and your server will do the work for you, which again is quite useful, both in terms of performance and if you just don't want to do that for whatever reason, right? Although having said that, I think implementing that in an application and not screwing it up is somewhat more difficult than what I've just described. So why do we want to use this instead of script? Well, it's much easier to parameterize. Generally, you're only going to be messing with the time and the maximum amount of RAM to be filled buttons, right? It's far simpler, as we discussed previously, right? Script was calling like 5 things. So, it needed PBKDF2, which in turn needed HMAC, which in turn needed SHA-256, or, whichever SHA you're using. And it also needed Salsa 28 code as well, right? This only needs itself and Blake2B. You can actually switch out Blake2B for whichever pseudo-random function you want to use. But again, it was designed as a package. So you probably just want to stick with that, unless you really know what you're doing. Again, we've got the data independent and dependent modes as well, alongside your client server handoff and your native hash upgrade, right? And the security analysis that's done on this, particularly because of point 2, right, is much simpler. It's much easier to cryptanalyze this function and Blake2B than it is to cryptanalyze SMIX. We just saw that Romix had a side channel on it, right? And this has been cryptanalyzed. So this paper came out in March, I believe, and they basically figured out a method where you could run Argon 2 with about 4 times less memory. So this is why we're at version 1.3 of Argon. So there will be vulnerabilities and there will be problems in your cryptographic primitives probably at some point. So you will have to check and make sure that you're always running the current version of this, right? So actually I believe the paper was January because the tweak, according to my presenter notes, was done in March. So that makes much more sense. Essentially the problem that they had was that when they were filling the 2D array in memory, and rather than overwriting the previous blocks, they were simply replacing them, which introduced essentially a side channel which allowed for a time memory trade-off attack. So it is being cryptanalyzed and it is being continually improved. So you can pretty much use this wherever the hell you want. There's bindings for it and basically everything. The reference implementation is on their GitHub. You can, if you're crazy, go look at the C. I don't want to look at the C. Don't even want to look at the Python, to be honest. But yeah, so please go use Argon 2 if you are designing applications that take passwords. Or if you happen to be designing a cryptocurrency, you might want to consider this, right? So the last sort of problem, so great, we now have some great memory hard hash function for storing our passwords, but how do we get from the old rubbish of MD5 and SHA, and if you're doing something really crazy like Adobe, to the new one, right? So I have to give Gavin Holt a big shout out here. He actually told me about this at SteelCon. So the Python Django web framework basically nails this. You basically take the old SHA-1 hash, and then you run that through your new function. So Argon 2, PBKDF2, or whatever, and you get a free puppy in a bag. Basically how this works is when your user logs in, you check the Argon 2 of the password, and if you don't have the Argon 2 of the password, you then fall back to checking for the Argon 2, the SHA-1 of the password, right? So that's without user login. So obviously once your user logs in, gives you the password, Again, you can then just run that through straight argon2, and eventually over time you will go from having a mix to predominantly more, and at some point you can call time on your old hash function, right? So yeah, I think that is actually the last slide. Yes. So if anyone has any questions or just general insults, please fire away. Oh, so.
Any more detail on the client-server handoff for the IoT devices?
I didn't really look into that much. It's listed as a feature, but I believe the RFC expands on it slightly more. It's not an entirely new concept. I believe Argon 2 is the first to actually implement it, but it's been sort of kicking about as an idea for a while. Hi, any questions? Yeah. Right, well, oh.
Yeah, so it's generally against using hashing to store the password, not just with Argon or anything. So you were saying the scenario of LinkedIn breach or something. Any breach happening, password is going out. That's the main scenario. So most of these breaches, the attacker is able to get into the either web server or database server and then the database. Maybe he run hashcash or whatever his tool and he cracked the password. But in reality, when consider LinkedIn example, you have a login function. So even if you use Argon 2 and the attacker is not able to crack the password with his hashcat or any of the tools, what may be custom tools, he can customize the authentication controller of the LinkedIn function, and he can make, okay, if user password equal to the input password equal to the hash, then save to a log or save to a new database table as a plain text. So he can even, he may need to wait some time to get all the data, but still he's able to take the password. So he don't need to worry about what hashing mechanism they are using. If it is a powerful hashing, I don't need to crack the password. I can same time, to customize functions, store the password plain text in some other file or database or anywhere. So
yeah,
do you have any better protection mechanisms such scenario?
I don't. I do not do web apps. I just do the back-end crypto. But no, if your attacker is, this is only helping you if you're talking about, the database getting hacked out and then, the password cracking forum people sitting churning away on their GPUs. It's not gonna, as you say, it's not gonna help you against, a malicious login function or anything like that. Yeah. Anyone else? Sweet. Thank you, guys.